Yeah, so hey everyone. So this is sort of a continuation of a talk I gave a little while ago. I think my talk on Friday at the Modular Summit will be an extension of this. But you know, maybe one of the biggest questions that comes from either the analysis of how people are behaving or you know, what seems to be true in practice is that cross-chain mechanism design is a lot harder than it looks. There's a lot of things that don't go exactly the way you think, and we've seen a bunch of people fail, so maybe it's good to kind of take a little look back at what things make this hard. So, as many of you might know, MEV is very hard to define formally, so I'm going to use a quite simple definition, which is MEV creates economic payoff uncertainties for unsophisticated users due to more sophisticated user actions. So it's a lot of words, but I think there's a way to think of it as living on a spectrum. So there's a lot of different types of uncertainties that blockchain users face. The one that everyone talks about the most, it's the easiest to understand, is ordering, reordering, getting front run, and increasing a particular user's economic return or payoff at the expense of others. The second type of uncertainty is sort of censorship of transactions, censorship of delaying transactions. And this is certainly one that I think people have come to realize that classical blockchains having only guarantees of being eventually consistent, eventually your transaction gets in, is not totally sufficient for a lot of different applications. You really need to have some bounds on how long it takes to get your transaction in. In the cross-chain world, I think one very important thing that doesn't really exist in the single-chain world is the uncertainty due to lack of atomicity. So, if you look at, say, liquidations on Compound or Aave, there's very few liquidations that are cross-chain, even though for some of the synthetic assets, it would be cheaper to go across a bridge or liquidate a cross-chain. Part of the reason for that is the lack of atomicity means you sort of can have unbounded losses. And we saw that with the Nomad hack, that there were some of the cross-chain liquidation stuff was huge losses. And then the last two, which are becoming increasingly important, are relay uncertainties, so networking layer attacks, so like the April 2023 malicious proposer attack. And finally, of course, data availability. Now, you might say, what is this arrow? What's the axis? I'm giving a stylized version of it, but you have some notion of a payoff. Payoff represents what value a user expects out of a particular application. That's the function f. We have a class of possible payoffs. That's the fancy-looking f. We have some notion of uncertainty, and we have some functional that takes a payoff and uncertainty, and we look at the worst-case behavior of that functional. OK. So what is cross-chain mechanism design? Cross-chain mechanism design is, the real goal is any class of mechanisms that reduce uncertainty for users given a payoff class. So this is trying to make a more statistical definition of what this process is, partially because a lot of the guarantees you expect in classical mechanism design don't exist. This has a lot more complicated trade-offs than a single chain, in the sense that reducing one type of uncertainty might cause another type of uncertainty to increase. So PBS might reduce inclusion uncertainty for certain parties while increasing relay uncertainty. These optimal guarantees that people have for single chains might just be completely impossible in cross-chain. Again, the atomicity piece is an example of that. And in some ways, cross-chain design is more like statistical learning than like classical mechanism design. So, I think if we look at the types of mechanisms that have been proposed over the years, and we compare them by how much documentation they have, of course, auctions are probably the most well-studied, thanks to online ad auctions and sort of things over the last 10 years. We have some things where there's some amount of formal analysis, some amount of, hey, we've run this thing in practice and stress tested it. And then there's a lot of stuff that's mainly in blog posts that people fight about. And finally, there's certain things that don't even really have a definition. And as you can see, these cross-chain mechanisms vary a lot in sophistication, but the point of this talk is actually show that even auctions get way more complicated in cross-chain land. And if the most well-understood thing is messed up, don't expect the things that are barely understood to not also have problems. So yeah, the real question is cross-chain auctions are hard. People aren't really participating in them. So historically, auctions have always been harder. Auctions have been sort of abused by centralized entities in cross-venue auctions. This is from the recent case of Department of Justice against Google. But there's also sort of a sense in which there's a lot of reasons that different mechanisms don't really give you price guarantees or uncertainty guarantees, and that's only just starting to get studied. So let's maybe look at a little thought experiment that'll give a very simple explanation of why cross-chain bidding and auctions are very hard, and we'll just do something that's sort of the bread and butter of cryptocurrency, which is DEX arbitrage. Well, bread and butter since 2018. So here's the question. Suppose I have two DEXs on two different chains. Is it better to bid on the atomic trade, like I do the trade on chain X, I do the trade on chain Y, and imagine it's something like IBC, I can redeem one-to-one and I do an arbitrage loop? Or is it better to bid on each chain separately? So maybe I'm doing a DEX arb of arb OP on optimism versus arb OP on optimism, on Arbitrum. And one of those is synthetic ERC20, one is real. Should I try to find a decentralized sequencer who I can say, hey, can I buy both transactions from you? Or should I go to each sequencer separately? So let's see what this looks like. So we have two chains. There's a current price, P of t, Q of t, for without the loss of generality. Let's just sort of assume PT is greater than QT. So now I do the arbitrage. I sell some of the asset on X, receive some of the asset on Y, of the synthetic on Y, and then I do the trade on the other side and receive dx plus units of X. So this is sort of the arbitrage. Note that the price has to change, obviously. There's some slippage costs, some market impact, and we're looking at what happens when they equalize. So now you can say, okay, well, if there's an arbitrage, what's sort of the maximum amount of profit I can get? And we can assume that, hey, if there's no arbitrage, whatever price that's at is the price of the maximum you could have received, given these slippages A and B. You can think of A and B as like the Uniswap slippage function, curve, balancer, whatever. It could be order book, when then it's stochastic. But for simplicity, we're kind of abstracting that. So now you say, okay, what was my profit in units of X? And so in this case, I'm looking at a single bid. Assume I bid in units of X for both legs of the arbitrage, and I can write out the profit. Pretty simple thing. Now assume I bid on them separately, and you can write the profits on each leg separately, and then you add them together and get the final profit. So one question is, how much should you bid separately? So, don't worry so much about the math. It should be sort of simple, but the idea is you write the two profits. One is the profit where you bid once, that's P&L atomic. One is the profit where you bid separately, that's P&L separate. You look at their difference, and what you get is you get a condition on the arbitrage price. So if the arbitrage price satisfies a certain condition, it's better to actually bid in separate auctions. If the arbitrage price doesn't satisfy a certain condition, then it's better to bid atomically. So what this says is that there's no sort of one uniform best auction format for these cross-chain arbitrages. It depends on the slippage functions, it depends on the price. And so if you think about the world where everyone is telling you, hey, we need to have a decentralized sequencer so people can guarantee atomicity, this is an example that shows you that's not always true. Sometimes it's better to bid on two separate sequencers. So again, so this gets you to this point that, depending on slippage and price impact, there's sort of not a unique best auction format. And in the cross-chain world, I think it's a better maxim is it's better to usually be good for most payoffs, as opposed to always being good for one particular type of thing. And this is much less like classical auction land. This is much more like statistical learning theory, repeated games. All right, so how do you quantify this uncertainty? Without going into too much detail, because I know there's not too much time, you can formulate this as a certain type of regret optimization problem, and then try to figure out which auction format reduces regret over time, and then adjust optimally. And one thing we show is that you can kind of measure this sort of best in hindsight decision and choose a mechanism dynamically as a function of current market conditions. So you can find a sort of best auction format for this particular DEX ARB. So at a very high level, all I wanted to do in this talk was illustrate just a quick point, which is cross-chain mechanism land is extremely difficult to reason about in a lot of ways. One of the reasons is that there's way more uncertainties, and those uncertainties interact with one another. And things that you might think are well understood or really easy to understand are not really the same when you have to think about how they interact with DeFi. And this auction example I gave, the reason it's so weird is that when I do the trade in one place, I'm implicitly changing the value of the auction in the other place because I'm changing the relative price, right? In one sense, I'm bidding only an X. The other one, I'm bidding an X and Y separately. But the thing I'm bidding on changes the relative ratio of the price X to Y. And so it means these auctions are sort of coupled in a very weird way that is not sort of what you normally think of. And so from this standpoint, you should really be thinking about these problems more from a sort of online learning or control lens rather than the classical auction design. Cool. And with that, that's it.
Question. So in the auction setup, how do you define the auctioneer role? So in a traditional world, you have an auctioneer and you have some regulations, you keep it. But in this, who takes the bids and how do you basically unbiased?
So if you look at MEV auction right now, the proposer at a certain slot is auctioneer, right? They accept the bids from all the block builders and they pick the one that wins.
But they get it from the relayer.
Yes, they get it from the they get the bid value from the relayer and the proof that the.
But normally auctioneer gets it direct, right? In traditional sense. Yeah, bid and sell.
Not always. There exist auctions that have escrow, where there's an escrow agent who, like art auctions, for instance, like Sotheby's is the escrow agent. They're technically not the seller, right? The seller is whoever owns the piece. Here, you're just making the relayer sort of your escrow agent, effectively. But in the sequencer case, it's the sequencers themselves are auctioning slots. Those slots are.
Yeah, because there's no block.
Well, there is. I mean, they are auctioning for that particular.
It's like first come first serve, the sequencer. Like, there's no consistent block time involved. So.
Well, some of the rollups are going to have their own auctions, just like MEV Boost. And so in that case, again, the sequencer becomes a auctioneer. Yeah.
Thanks.
Mark.
Yeah, if we kind of dealing with this mechanism design problems like control loop, what are the kind of disturbances that would kind of define like what you need to tune for?
Yeah, so in this example, right, there's this kind of interesting thing where the no arbitrage price interacts with the relative bids of the two different auctions. And here, the signal you're getting is like the current no arbitrage price, and the output is the relative bids. Like you could think of it as, you could think of this thing as sort of quantifying the ratio of the atomic bid to the single bid.
On each of the separate domains like affect like how sensitive it is?
Yes, so that's captured in the fact that when I computed this P star is defined by these slippage functions, right? It's like if I sell on the one that's more expensive and I buy on the one that's less expensive, and I realize these slippages, I'm at the optimum price if they're equal, right? So it does depend on the liquidity conditions. And so that's the key point. Like the auction format that's optimal depends on the current state of each system.
So it would be like a composite, like switching between like
Atomic versus not. Yeah. that's why I think it's kind of interesting to point these things out, because everyone seems to be being like, okay, well, we just need like a decentralized sequencer, or we need a shared sequencer that can guarantee you atomicity. But it's not even clear that the atomicity is worth as much as it is in a single chain. Well, the shared sequencer is auctioning the arbitrageurs the right for that particular slot, right? My point is more that the shared sequencer, the arguments people make for shared sequencers are guaranteed atomicity, right? Like I have arbitrum, I have optimism, I can guarantee you atomicity. But the weird thing is that the atomicity might not even be worth it. You might actually want to bid on these things separately, right? And so there's sort of this very interesting behavior that happens when the thing you're bidding on changes the price of something else you're bidding on another, in another place, which is not true.
Is it feasible to actually determine which one is the right thing, like in time, like to deal with these scenarios?
Yeah, so you could imagine the shared sequencer themselves was computing this and offering you atomic or sequential at every round, depending on the current liquidity state.
Is that not like a computationally like taxing, like polynomial time?
No, I mean it's probably not. You can probably approximate it quickly.
I think it might be more towards the incentive compatibility issues rather than
Yes.
compatible.
Yeah, exactly.
Wouldn't the industry just move to separate options by default because people want to do their own thing? And
That's what you think is true, but if you go to any of the literature, everyone's talking about shared sequencers and decentralized sequencers that have this, try to give you these guarantees, right? Like,
so do you think that they're just trying to solve a problem that doesn't necessarily, isn't that important?
so I think part of the reason, if we're being 100% honest, that people are solving this problem is regulatory cover. They need their roll up to like look sufficiently decentralized. But in the process, they created these problems that have these weird incentive issues. That's the honest answer. I don't think any of these roll-ups will ever fucking tell you that, but that's sort of the real answer.
I guess it doesn't introduce unnecessary complicated logic, right? I mean, a separate option seems very simple to implement versus.
For sure.
Yeah, right.
For sure. But people also don't want to have to communicate with 500 sequencers.
But that's what the MEV guys want to do. That's the.
Well, I mean, right now, right, there's not that much cross-chain DEX arb, in fact, empirically, actually. And I think there were some people presenting that earlier today. And so part of the reason for that is this lack of atomicity guarantee, right? Like if there's a missed slot by a sequencer, you're off by a slot, say the Oracle price moves by 20 bips, you're screwed, right? So there has been a lot of kind of work on trying to analyze this. So, but. All right, if there are no other questions, thanks.